This is lecture 33 based on third unit for the subject digital signal processing, and in this lecture we are going to discuss about the FIR design using the Kaiser window method. Okay. So, in previous lecture we have seen this rectangular window, Hanning window, Hamming window. Now, the another one is Kaiser window. Okay, so we will talk about the basic concept of this Kaiser window, what is the window function of this Kaiser window, what are the steps for designing FIR filter with the help of this Kaiser window method. Okay, so let's start the some basic points related to this Kaiser window. So there are some points. Consider the magnitude specification of FIR filter as shown in figure. Okay, so this is the magnitude response of the FIR filter. So you can see here on x axis that is your frequency omega, and y axis that is your magnitude. Okay, so the filter function, whatever the function, the magnitude of it. Okay, so there are some designing parameters. Okay, we can observe with the help of this figure. So you can check over here, that is your del P, where del P is your peak passband deviation. Okay, and del S is a stop band deviation. Okay, so how this del P and del S is coming? So just draw the line on x axis parallel to x axis. So this value will give you the omega P, where omega P is the passband as frequency, and here is your del S. So this point will give you the omega S, and omega S is your stop band as frequency. Okay, so omega P, omega S, del P, del S we know, and after that this region is called the, from here to here is called the pass band, and the from omega S to rest is called the stop band region. Okay, and delta F equal to the basically this is the transition width. So transition width equal to nothing else the omega S minus omega P upon 2 pi. Okay, so if we have omega S, omega P, we can easily calculate this del F. Okay, now if we talk about this Kaiser window, okay, so the length of the Kaiser window is m plus 1. So you have to remember this, we are taking the m plus 1 length, and the design as the function is given by, for this Kaiser window is Wn equal to I naught in bracket beta 1 minus n minus alpha upon alpha whole square to the power 1 by 2 upon I naught beta for 0 to m, for n is lying from between to 0 to m, and the value of otherwise 0. Okay, so this is the function of the Kaiser window function. So here alpha equal to nothing else the m by 2. Okay, and this I naught x, because you are getting I naught beta over here. So I naught x is the Bessel function of the first kind, and obtained by using this equation, that is I naught x is equal to 1 plus 0.25 x square upon factorial 1 का whole square plus 0.25 x square का whole square upon factorial 2 का whole square plus 0.25 x square का whole cube upon factorial 3 का whole square, and so on. Okay, so this is the basic designing your window function. Okay, so window function. Now if I talk about this window function, you have required to calculate the beta also. Okay, because there are parameters unknown, beta, alpha we know how to calculate the alpha, Bessel function we know how to calculate this Bessel function value. Okay, now what are the designing steps for designing this digital filter or FIR design using this Kaiser window? So firstly you have choose the optimum value of del. Okay, so for del, that is the minimum value of del P and del S. So whenever you are going to calculate del P and del S, So what will be whatever the minimum value of between two, that will be considered as a del. Okay, where del p you can calculate with the help of del p equal to 10 to the power 0.05 ap minus upon 10 to the power 0.05 ap plus 1. Okay, and del s you can easily calculate with the help of 10 to the power minus 0.05 as, where ap is actual pass band ripple in dB and as is minimum stop band attenuation dB. Okay, so first step you have to choose the minimum value of del. So for calculating del you have required to del p and del s. So for this you can calculate del p and del s with this two formula. Now second step, to calculate the a, okay, in dB. So a equal to nothing else minus 20 log 10 del, because then we already calculated, so we can easily calculate the value of capital A. Okay, now for beta calculation, beta equal to 0.1102 a minus 8.7 when the a is greater than 50. So whenever you are going to calculate a, and if a comes greater than 50, then beta equal to this one, and if this a is lying between 21 to 50, then we have to consider this one. Okay, that is 0.5842 in bracket 8 minus 21 to the power 0.4 plus 0.07886 a minus 21, and for the rest values the value of beta is 0. Okay, so with the help of this we can calculate the value of the beta. Now the remaining thing is m. So this filter length m equal to m plus 1, where m equal to a minus 8 upon 2.285 del omega. A we already calculated, del omega we know that is omega s minus omega p. So with the help of we can easily calculate this value of m. So now you guys have all the designing parameters. Now whatever the function is given, okay, so select the desired impulse response depending upon the type of the filter which filter is given to you, and this is the same. Okay, the rest procedure is same whatever we have done in previous lecture. So hn equal to क्या होगा, hdn multiply with w1 is you have to multiply with this window function. So we will get the response of the your filter. Okay, now here one more term is came, that is Gibbs phenomena. Okay, so in window method we obtain the impulse response of desired FIR filter by Hn. We know if you want to take this in distal form, so this is Hn. So just take the your Fourier transform of this Hn, and we will get h e to the power j omega equal to h e d e to the power j omega into w r omega. Okay, so the frequency response h e to the power is j omega shown in figure. You can see here the same which we have seen earlier. So that is the omega and the magnitude response. So these are the your ringing function. Okay, so because there are oscillation over here side lobes. Okay, here due to this side lobes presence in the frequency response of the window function, the ringing observed in the frequency response of FIR filter, this ringing is mostly present nearby bandage and it is known as the Gibbs phenomena. Okay, so these ringings, okay, these oscillations over here is known as is your Gibbs phenomena. So these are the basic steps for calculation your FIR filter with the help of the Kaiser window. Okay, so you have just follow all the step from designing step from 1 to 6, and before that you should have knowledge about the this window function. Okay, window function of this your Kaiser function. Clear? So this is all about today's lecture. Thank you, students.